Hello, welcome back again into my channel. So this channel is dedicated for all engineers to get better knowledge and skill while using CAD, CAE and CAM software. In this video, I will show how to create a basic of internal flow simulation using FLOEFD for NX. For the beginning, I will introduce FLOEFD. So FlowEFD is an integrated CFD software inside an XCAD. So during the works, you're gonna use an XCAD interface. The key advantage is integrated with the CAD software. So it makes a very easy modification and multiple CFD scenario. For example, in this case, this is the valve. We have a sharp edges for the ball valve, and also we have the other design option using radius for this ball valve. So it means you can create a multiple scenario on the CFD simulation because it's integrated with the CAD software. And also next in here is automatic create fluid body domain by just make an airtight CAD geometry. So it will automatically detect the fluid body domain like this blue color shown in here. So you don't need to have become an expert in CAD editing in order to create a fluid domain. Next, this is excellent meshing and offer very simple meshing using smart cell technology. So the meshing is going to be like this. This is what we call a smart cell technology. This meshing also can be adjusted to have refinement like this in order to capture the small detail in the solid geometry. Next also is a robust CFD solver that error-free during calculation. So once the calculation is convergence, it will show in green color. It said achieve on iteration a number. For example, this one, number 106 and number 74. And also finally, SimCenter FLOEFD also using what is called a modified K epsilon turbulence model to simulate its turbulent flow. So that is the basic introduction of FLOEFD. For this study case, I'm going to use this part. This part actually I already used using SimCenter 3D to create internal flow CFD simulation about more than 2 years ago. I already upload this video using this CAD model. So in here, the FLOEFD case is the inlet is environment pressure from open air as if enters here, and then the outlet, the total outlet in here is 0.1 kilogram per second. Meanwhile, for the simulation data, this is a material, the cast iron, the inner surface roughness inside in here is a 50 micron. Type of fluid is air. Analysis type, internal flow. The simulation type is steady state. Flow type, laminar and turbulent. Standard of gravity, 9.81 meter per second. The thermal condition is adiabatic. Okay, for the simulation setting, in here, you can press Ctrl Shift F button to start FlowEFD application inside the NX. So after that, you can create a tree like this. Now in here also, I'm going to show you how to create a global mesh setting using level 4 refinement and how to capture 0.01 meter feature. For example, you have a gap, slot, etc. And then apply advanced channel refinement. For the equation goal, we're going to create the expression of our formula. The formula is pressure drop is outlet pressure minus inlet pressure. And then I'm going to show you how to create the meshing result and also the refinement level. Next, after we do the calculation, I'm going to explain a little bit about the running calculation and convergence. So this is the window after the convergence. And then on the tutorial, I'm also going to show you how to create this one, a mesh contour check and pressure plot animation like this one. Later, I'm going to show you how to create flow trajectory and surface parameters. So we're going to extract this one, inlet parameters and the outlet parameters. Next, I'm going to show you how to create this one, what is called the velocity profile on the inner surface in here. As you can see in here, the velocity near the wall is 0. Meanwhile, at the center, the velocity is almost maximum. This is because we have the roughness for the inner surface is 50 micrometers. In this video, I will demonstrate how to create a CFD simulation using FLOEFD for NX. So now in here, we have a part. This is a hole, the top in here, and also we have a 5 holes in here, and we have a single hole in here. So now let's begin the FLOEFD. You can press the button to control Shift and F. So this will start automatically for FLOEFD for NX. In here we have a navigation for FLOEFD, this one. So this is the tab of flow analysis. This is the FLOEFD flow analysis. Now in here at the beginning, there's a called a wizard. Okay, we can click the wizard. Now appear in here is called the project 1, so you can rename it with your own preferred project name. And then we can go to next. This is the units, so you can change the units. For example, you can change the mass, something like that. And then also loads and motion in here. For example, the mass flow rate, kilogram per second, you can change, and so on. Next, we have in here what we call the physical feature. So we're going to create just only CFD simulation for fluid flow. So we can check this, the checkbox become active. Next is the analysis type is internal. So I'm going to change become internal. The given recognition is cat to boolean. And in here, maybe I just uncheck this one, extrude cavities without a condition. And then click next. Now, we will define what's the fluid inside this. So in here, maybe I'm going to just add the air as a fluid material that we're going to simulate in here. And the flow type is laminar and turbulent. Click next. And then we can add the roughness inside this, so we can get some kind of velocity difference between the center and near the wall. So I'm gonna add in here, for example, 50 microns for the roughness. Then I click next. In here, no change. I just click OK and click finish. Yes, often create lids. So we're gonna create some kind of lids to close all the holes in here. So as if we're gonna create the airtight volume. Do you want to create open lid tool? Okay, click yes. Okay, in here, select planar faces to the opening volumes tool. We can click this one. Okay, so it will create some kind of a solid geometry to close this hole. This is the default thickness, but you can change in here to adjust the thickness. No need to too thick, because this is just to make the volume is airtight. So we can click OK. In here in 2 millimeters. This one, okay. For example, if I click no, okay. Let me show you what is create lid. Before that, this is what we call a computational domain, so we can hide this one. Okay. So in here we actually already create the lid, but it's not shown. I can show in here. We can go to view, show and hide. We can hide all and then show again. Now this is the lid. Okay, this is the lid. Now in here is still open, so we need to close in here also. So we're gonna make it airtight in here. So we go back to this FLOEFD, this one, this tab, flow analysis. This is the feature we created this lid. Okay, click this one. But just notice it's just only affected to the planar faces. Okay, so the curve you must create your own solid modeling. We can click this one, this also we can close, and also this also we can close. Maybe we can adjust the thickness, become just only 2 millimeters. Okay. Yes, I set the consideration. Yes. Okay. Now we're gonna see again the lid is hidden. We can go back to view, show and hide all the solid body and show again all the solid body. So this is the lid we created. This one. We can delete the unnecessary lid. For example, like this one, we can delete. This also delete because this one is just only for the four holes, right? There's no flow in there. And then we can click close. Click close this one also. Yeah, we can delete this. Delete, delete. So now we have an airtight volume inside here. So this is gonna be the fluid domain for the simulation. Now in here, in order to validate this, we need to use this one, what is called check geometry. So in here, this is the tools to create the fluid domain automatically after it become airtight. So let's check. Okay, this one it said successful. This is fluid volume, this is a solid volume. Then we can show the fluid volume. So this is the fluid volume inside this part that we're gonna be used for CFD simulation. So the good advantage of this FLOEFD, it can create automatically a fluid domain without need too much CAD editing. So this is the great capabilities inside FLOEFD. Okay, we can click OK this one. Now we can continue to create what is called the boundary condition. So right click this one and then insert the boundary condition. In here, we're going to create this one as an inlet. Meanwhile, this four surface become the outlet. So we're going to create the inlet, the pressure opening, environment pressure. So we can click this and then make sure the window in here appear like this one. So we can select the inner surface of the lid like this one, right? Okay. Then this environment pressure and then click OK. Now in here, if you want to see what's inside the symbol, I can go here to display, this one, edit object display, click OK. For example, maybe change the color, make transparency, okay, and then click OK. So this is the symbol, the environment pressure, this one, okay. Next, we can create what it's called. This is as the outlet. Click again, insert boundary condition, and then here as the outlet mass flow, and the outlet mass flow is 0.1 kilogram per second for these four holes. And then we can click the inner surface like this one. Click this. Number 2, number 3, and then there is number 4. So the total for these four holes is 0.1 kilogram per second. So this is the outlet. Okay, this is the symbol of the outlet. Okay. Okay, so this is the inlet and outlet boundary condition. Next, we're going to create goals. We insert what is called a surface goals. So the objective of the surface goal is to create what it's called using it as a convergence criteria. So maybe I will expand a little bit in here. In here, use it for the convergence criteria. Okay, so for this one, I'm going to just click inlet environment pressure in here, and then what I need to check in here is the total pressure So click the average in here. So we're gonna inspect the average value and use it as a convergence criteria. And because this is one as an inlet, we can add this one. So SG is surface goal, inlet parameter number. Click OK. Now it creates as SG inlet average total pressure 1. And then I'm gonna create again insert surface goal for the outlet. I just click this one and then click the total pressure average as a parameter need to be checked for the convergence criteria, and then I give this also SG outlet. Click OK. So in here we have two, inlet average and outlet average. Next I'm gonna create what it's called equation goal. So we're gonna check the pressure drop. This expression is the formula for pressure drop is SG outlet minus SG inlet. This is the formula, and then we can click OK. Next, we're gonna create the mesh. So in here we have what is called the global mesh. If I double click this, it have two options, automatic and manual. And accuracy, we can change the level of the mesh in here, the level of initial mesh. For example, I can click this one to show the basic mesh shape and size. This is the level 3. If I reduce become level 2, it's gonna be a bigger like this, so it's less accurate. So if you want to increase the accuracy, you can change become level 3 and level 4. Okay, and then in here we have what's called minimum gap size. So in here, for example, if I put in here 0.01, it means if the gap is less than 0.01 meters inside this solid CAD model, it will be ignored as if there is no gap. But if we have the gap is larger than 0.01 meters, it will consider as a gap and the mesh will be filled in inside the gap. And also in here, we have an option what is called the advanced channel refinement. Then we can click OK. Now we are ready to create a mesh. In here, this is in the flow analysis, you can click Run. In here, the option mesh and solve. So what you need to do is to uncheck this one. Okay. The cost and the memory usage, we're gonna use all. So in this computer, we just only have 16 cores, so we're gonna use all. And then we automatically load the result and then click Run. Now we have the result. For the mesh, we can, for example, in here we can insert to check the mesh refinement. You can use the section in here, XYZ plane. Click this one, okay. And then you can see in here the refinement level. And then we can click apply to see. Now this is what we call the refinement level. Using this arrow, we can pull like this one. And then for the preview, we can automatically preview like this. Okay. So it will be something like this. So this is the refinement level. We have a 4 refinement level. Now in here you can see this is a 0 refinement level. So this is the a basic size of the global mesh. Now it also reduce the element size and then reduce again. This is level 2 one. Okay. Meanwhile in here is a level 1. In here is the level 3. Now let's check for the level 4. Let's pull this. Now we found in here the level 4. So this is how to check the refinement level on FLOEFD. You can click OK. and then we can hide this from the display. Click hide. So it means in here we are ready for calculation. You can click run to start the calculation. Because we have already have the mesh, so no need to check this one to the mesh. We just only click this one, solve, and then this is new calculation because there's no calculation yet. Okay, and then we run the calculation. Now for the calculation, you can see in here we have the goal plots in here. I can click this one and then I can click OK, so it will show this one. And then we can also change the scale, become normalized scale, so you can see this is how FLOEFD start the calculation. Okay, it will start like this and it will show the curve or the graph like this. Okay, so this is the goals: pressure drop, SC inlet average, and SC outlet average total pressure. So this is the goals that we already create for convergence criteria. Now, after the calculation completed, the progress in here is set achieved at iteration 74. So if you found this one already green, so it means all the in here the goals is convergence, and it said the solver is finished. This is the number of iteration. So it means in here the calculation is completed and the result is automatically loaded into this simulation model. Okay, since this already finished, then we can continue to check this one, what is called cut plots. Right click insert, and then we can select this one based on the X, Y, and Z planes. Maybe in this, make sure it cut the geometry, and then you can select what need to be shown in here. And you can also increase what is called number of levels. So for example, in here, if I click this, it showed the pressure, this one. Okay, let me hide delete first. Okay, okay, so this is the pressure plot. As you can see in here, where this pressure plot is just only have a 10 levels, the color is quite rough in here, so you can increase this one. So in order to create more smooth of the gradation of the color itself. So in here maybe I'm gonna use the maximum 255 and then I click OK. So now it creates the smooth gradation for the color. And then because we already complete the calculation, in here we have the button what's called play. So it will automatically create like this. It will sweep along inside the fluid domain that we already calculated before. So you can check the pressure in here. We can click again to stop. And also in here, you can change. In here we have the pressure. You can change become the velocity, like this one. It will change like this. So you can change what you need to see in here. And also you can see there's a lot in here. Maybe this one, acoustic power level also. It will appear. Then click play again. So this is the acoustic power level, the noise. Okay, so this is the function of the cut plots. Okay, we can hide this one. Next, we're going to create what is called flow trajectory. Click insert, and then click the source. The source is from the inlet. Okay, and then there's an option in here, For example, I'm going to use the arrow flat first. I will show you like this one. This is the arrow. The arrow seems too small. Let's change become the velocity in here. Okay, and then we can increase the arrow size. Oh, it's too big. Maybe we're gonna reduce it again. Now we can show in here. Okay, this is the uh, what is called the flow trajectory, and then we can play this one. So this is flow trajectory, how the fluid flow. And then also we can change this one, not just only flat arrow. We can use also the 3D arrow like this one. Okay, and also we can change become the pipes, something like this. Also the lines, and also the line with arrow. Now this is line with arrow. If I play the animation, you can see in here, so you can see the trajectory and also the arrow direction. So this is the how the function of the flow trajectory. This is the velocity. Okay, let me stop in here. The next is surface parameters. So surface parameters is to investigate from the inlet parameters and the outlet parameters. For example, if I click the inlet total pressure and I want to check the mass flow rate, the pressure, maybe the density, for example, the velocity, of course, and also the volume flow rate, maybe in here. And also I want to check the dynamic pressure, maybe, and also the Prandtl number. And then I can click OK. So I need to rename it first as what is called inlet parameter. You can rename the parameters. Okay, and then you can click show. This is the inlet parameters. You can drag it like this, okay, for the positioning. So this is the inlet parameters. You can extract the data, and then also for the outlet parameters, just right click and insert this one, outlet FS parameter. You can take SMS like this one, the density, mass flow rate, the pressure, and also the velocity, and the this one is dynamic pressure, the total pressure, okay, the Prandtl number, and then I'm gonna rename as outlet parameters. And then I can click show. So like this one. Maybe I'm going to change this display back again, so there's no translucency. Okay, so you're gonna can see it's clearly now. So this is the inlet parameters, and this is the outlet parameters. So you can extract all the data, the inlet and the outlet. Next, I'm gonna create a velocity profile. Let me hide this one first. Also hide this one, this flow trajectory. I'm gonna create what it calls the XY plot for the velocity profile here. But before I create this XY plot, I need some kind of line. So I'm gonna go back in here and then I'm going to create a line. So in here I'm going to find into the edge this one. Okay, so this is the curve I'm going to create as a guidance for this XY plot. And then click insert for the XY plot, select object, select this curve. Okay, curve is line 23. What I'm going to show you is the velocity profile on this hole. Then click show. Now you can see in here, this is the velocity profile on this hole. Near the wall, you can see in here the velocity is 0, right? Also, in here the velocity is 0. Because we have the roughness wall in here, the roughness is about 50 microns. At the beginning, the simulation we already defined as a rough wall. So it means the velocity must 0. So in here also the same, the result, the velocity at the wall is 0. And it increase rapidly, become the highest velocity in here. So this is how to create a velocity profile in the holes, for example, in this one as a internal flow. So that's it, how to create FLOEFD simulation. And as a notice for me, this part is exactly the same. I create the CFD simulation using SimCenter 3D, the video that I already uploaded more than 2 years ago. Okay, I hope it's going to be useful for you, and thank you for watching.